Okay, so looking at polarity of a cell, the first thing I like to look at, and I will say for pathophysiology, I think with everything we do in classes, we're trying to put all of it together, which eventually with pathophys you will, but with how they have it outlined, I would personally try to not put everything together, if that makes sense. So like, for me, when I look at this, I immediately start thinking of which cell is being polarized, what the problem is, all that kind of stuff. Try not to focus on that just yet, and just think of a cell and electricity. Because when you try to put everything together with how much they're putting into these required readings, it's too much, and it doesn't come together because they're not necessarily putting things in order. Like we have cancer with polarity. Anyway, that's just like my take on it, but let's start with ions. So with ions, that basically means a molecule or atom that has gained or lost electrons. And remember that electrons are negatively charged. So anions are going to gain electrons. Since electrons are negative, if they gain them, it creates a negative charge, which seems counterintuitive, right? If you gain, it creates negative. But we're talking about charge, electricity. A good way to remember this: a negative ion, a negative ion, anion. That's going to include your chloride, your bicarb, phosphate, and sulfur. We shouldn't really go into these too much, but these are the main things that are going to make your cells in that resting potential, which we'll go into more. So focusing more on the cations, and please excuse my writing, it's very bad. So the ion has released electrons or given them away, which creates a positive charge because now we have less negative, oh my gosh, what are they called? Ion particles, atom particles, oh my gosh, I can't remember. Anyway, it's negative. Way I remember this, when you spell out cation, the T becomes a plus for positive. So helps you remember a negative ion and positive. And that's going to be our main electrolytes, which is your potassium, sodium, calcium, magnesium, and hydrogen. So I will make a note and say that calcium really threw me off, and I still don't fully understand it, but we'll kind of get to that. And it does kind of talk about why each one is important, but basically just know, like, the most common you're going to be dealing with are potassium and sodium when it comes to like electrolyte imbalance. These, obviously hydrogen goes into acidosis and all that kind of stuff, but really even in the writing it really only talks about hyperkalemia or hypokalemia and hypernatremia, hyponatremia. So if we go to a hyperpolar state, I've kind of drawn out little like, think of it as like a scale. So if this is neutral, right? At our resting membrane potential, we're at negative 90 millivolts. That's because of these, right? Your anions, your intracellular anions. That little picture that she put on the paper it was the dashes, which made no sense to me. So just know that there's more of these than there are of these in a normal resting. We didn't touch it, it's just their cell. So for normal cells, which means cells other than cardiac cells and brain cells, because they actually have a different charge. But in normal cells, your resting potential is 90 millivolts. Your action, or your threshold for action, or the voltage that is required to be met for the cell to do something, is at 30 millivolts. So we have to at least get here to do anything, right? So that's what, 120, if I do math right? Yeah. So there's 120 millivolts that's needed in a normal everyday cell for it to do anything, right? So if we are hyperpolarizing this cell, it actually kind of messes with it and brings it lower. So all of a sudden your general resting is at, let's say, negative 120. I think that was the example given. Now, where this gets confusing is, obviously it says hyperpolar, but we're going down. And the biggest reason that it is hyperpolar versus hypopolar is because if you look at this gap, this action potential gap is what I'll call it. I don't know if that's what it's called, but this gap is widening, right? Or it's getting bigger, or it's hyper, right? So it's hyperpolarizing because the difference between the resting potential and the action potential has become greater. Examples of this, honestly, the ones that come to my mind are benzodiazepines, Xanax, Ativan, anything like that. That basically, what that does is binds to a specific receptor in the brain that allows a ton of chloride ions to flow in. Since they're negative, it drops the action potential, right? So even though we're going to ignore that I just said that those are different voltages, it drops it from like negative 90 to negative 120. So all of a sudden you're having to use way more cations to have anything happen, right? So you're going to have lethargy, or basically like they're just not really with it. They're kind of slow. If it gets bad enough, like they overdose on it, same with opiates, obviously it's going to create such a wide polarity that there's nothing, we can't use enough cations to get to the charge that we need to. I will also say, it says that it in the reading that it changes the it changes the resting potential, and while it does, it's not a permanent change. These cells are highly sensitive. The body's super sensitive. It does not like any state outside of normal. So keep that in mind, where like there is no, it says it like changes it like I read it as permanent. It is not a permanent change. It wants to go back to that negative 90, whether it is hyper or hypopolar. So the more common one you're going to see is that hypopolar state, where something happens and all of a sudden we increase our voltage. So now we're gonna say that this is -10 millivolts. Now, instead of 120, we have 40, right? I just realized this is a negative. Ignore that. This is positive. So obviously, anytime you reduce a number, it's going to get there faster, right? And that's where your hyperactivity comes from. So again, keep in mind that this gap shortens or becomes hypo. So even though it feels like an opposite reaction because your voltage is going up, but your polarity is going down, it has to do with this little gap, right? So we have a lesser gap, you're going to see increased activity. So muscle twitching, that one, that's the biggest one. But basically, like, it's going to make them feel very agitated, very not right. The most common ones you're going to see with this are your hyperkalemia and hypernatremia. So too much potassium, too much sodium. And those are going to be mostly like your diabetic and in-stage renal disease or dialysis patients. So not always, but it is what you see quite a bit. And I say diabetic because they go into diabetic ketoacidosis. Again, remember our hydrogen, or what causes acidity, is a cation. So keeping all this in mind, another thing I will say is one of the things that I got asked on my national registry for my paramedic license was about the prominent cation in the intercellular and extracellular, right? So an easy way to remember that, I don't know if that's going to be asked. It's just something that, like, I feel like will be asked because I got asked so many times. So if you have a cell and another cell says to it, hey, do you want to go to Circle K? That cell says, nah. So your extracellular cation is sodium, intracellular is potassium. That matters mostly for things like your sodium potassium pumps. Remember, that takes ATP or energy to do so. So regulating all of that becomes a lot harder than others because some are diffusion, which takes obviously no energy. Now, the special note on calcium, I honestly have no idea why. Like, I wish they kind of went into that a little bit more, why calcium creates this state that it does. But they did say that anytime calcium is one way, it causes sodium to go the other way. So I'm going to use hypopolarity for our example. So with hyperpolarity, you have hyper K, and then hypernatremia. I always feel like I'm spelling those wrong. But then you have hypocalcemia, which kind of throws that off, right? But we know that this has a direct inverse action on sodium, right? So anytime this is low, that's going to create a state where the permeability for sodium is going to be, it's going to increase permeability, which just means like the ability for it to cross into the cell. So basically, like, the way I see it is hypocalcemia is the same thing as hypernatremia, simply because it becomes that, right? So then you just kind of remember it as all your hypers, right? So hyperkalemia, hypernatremia, hypocalcemia slash hypernatremia is all going to be in your hypopolar. So on your card, your memory aid, there we go, think of it as everything either in the body, it either potentiates or it does the opposite. So this time we have our opposite effects. So hypopolar equals hyperactive. Hypopolar equals hyper, and I'm just going to put cations. That's not a word, but you get my point. So remember, this is an inverse reaction. One goes up, the other goes down. Most things in the body are going to be that way, where it's a compensatory mechanism where if one thing shoots up, the other thing goes down. Another thing that does that, blood pressure and heart rate. For every point your systolic goes down on blood pressure, your heart rate goes up by 1 point. So just, you don't need to remember that, but I was just giving you an example. So basically, if you can remember that it's an inverse reaction and that the name of it has to do with that gap, those are your two biggest things with hypo and hyperpolarity. And then hopefully as we continue and start getting into disorders and everything, I can go into it more and explain like why it matters and everything. But for right now, that is the basis of polarity of a cell.